The last reaction is the reaction on the beta carbon of a conjugated system. So if you have a carbonyl and that carbonyl is conjugated with the double bond, then in this case, if you have a nucleophile reacting, depending on the strength of the nucleophile. So if the nucleophile is a weak nucleophile, and this is the list of all the weak nucleophiles, then the weak nucleophile is not going to attack the carbon of the carbonyl. It's going to attack the beta carbon, form a negative charge on this carbon. We call it the enolate. The solvent will protonate the enolate, and you are going to get your product. So if you look at your product in here, what I did is an addition on the beta carbon. So I added my CN on the beta carbon in there. I did not add my CN on the carbon of the carbonyl. This only happens whenever you have a conjugated system that is directly connected to the carbonyl. If you don't have a conjugated system, then definitely the CN will attack the carbon of the carbonyl. But if you have a conjugated system, then the CN will attack the beta carbon, form a negative charge on the oxygen. So this is why you need a solvent with all of those in order to protonate that negative charge. This is called an enolate. You're going to protonate it, and you're going to add a hydrogen over here. I'm just showing you here the difference between those two reactions. Here I don't have a conjugated system, so in this case the CN attacked the carbon of the carbonyl, formed a negative charge on the oxygen. This proceeded by the cyanohydrin reaction that we've talked about earlier. The negative charge will be protonated by the water, and you're going to get your cyanohydrin. Same thing if I have any of those nucleophiles in there. If I also have an RSH, let's add this one out because I have an example of this one over here. So this is the RSH. This is a weak nucleophile. So this is not going to attack the carbon of the carbonyl. It's going to attack the beta carbon, form a negative charge. You protonate, and you're going to get your product. Any ammonia and its derivatives, any derivative that are made up of nitrogen, those are weak nucleophiles, and those are going to come and attack the beta carbon. So let's say, for example, hydrazine. Hydrazine is an example of an ammonia derivative. So this one is going to come, it's not going to attack the carbon of the carbonyl, it's going to attack the beta carbon, form a negative charge, and then you are going to protonate. Because this one is a base, you don't need to protonate. The nitrogen is already a plus charge. So you can do a hydrogen shift in this case. And you can get your neutral product. There's a difference between those two reactions because remember with this one over here, this is a primary amine. You're going to end up getting your imine because it's not a conjugated system. So here I'm going to lose 2 hydrogens and oxygen. The attack is going to be on the carbon of the carbonyl. And you're going to get your imine product. Organocopper reagents also, this is the R2CuLi, this is the Gilman. So with the Gilman, this Gilman releases carbon ion. This is a weak nucleophile. It is not a strong nucleophile for these types of reactions. So the Gilman, in this case, the R is going to come attack the beta carbon, form a negative charge that gets protonated. Another nucleophile is the diethyl aluminum cyanide. The CN is a better nucleophile than the ethyl group. So this is why the CN is going to add over here to the beta carbon. It's going to add, form the enolate, and then it's going to get protonated in there. So this one is more nucleophilic. This is why it's going to add compared to the ethyl group in there. This will all attack the beta carbon. On the other hand, this is the list of the reactions that we've been talking about in this chapter in here. If you have a strong basic nucleophiles, then in this case, the reaction is going to be on the carbon of the carbonyl. So Grignard, alkyl lithium, the reduction reactions, sodium acetylide, all of those are considered to be strong nucleophiles. So even if you have a conjugated system, the attack will not be on the beta carbon. The attack will be on the carbon of the carbonyl. You're going to form a negative charge on the oxygen, and then you're going to protonate. So the reaction is going to be on the carbon of the carbonyl with this one. It makes sense because grignards are very reactive together with alkyl lithium. These are strong nucleophiles, so they have to attack the carbon of the carbonyl in order to get the alcohol product. Same thing for the sodium borohydride, lithium aluminum hydride. The H minus does not attack the beta carbon, it attacks the carbon of the carbonyl. Over there, this is a challenging problem of the acetal formation. So you have a carbonyl and you have NOH, and you are first reducing. LAH is lithium aluminum hydride. Okay. We've talked about this reaction. We said that this reaction is a strong reducing agent. It reduces it releases the H minus in there, and it's going to reduce the carbonyl into NOH. So the first step, the H minus is going to attack the carbonyl. Notice it did not attack the beta carbon. It attacks the carbonyl because it is a strong nucleophile, reduces the carbonyl into an OH in there. And now after it reduces the carbonyl into an OH, now I'm going to go ahead and react. This is two OHs, two alcohols. So this is a reaction of the acetal formation where you're reacting two alcohols in presence of an acidic medium, and you're reacting those with the carbonyl of the ketone. So to proceed with these reactions, if you want to get to the product directly, the OH is going to lose a hydrogen. So you have your oxygen in there and the oxygen in there. Both of the alcohols are going to lose a hydrogen. So you take the hydrogen away, and then you look at the carbon of the carbonyl. You make a bond with the carbon of the carbonyl, and then you put whatever groups you have on the carbon of the carbonyl on this carbon. So this is going to be your acetal product.